So next speaker is Marion Douspis from IAS, and he will be talking about cosmological constraints from the Planck SZ cluster counts.
Okay, good morning. I'm really glad to present one of the results from Planck, cosmology from SZ cluster counts, on behalf of the Planck collaboration. As you know, it's a big collaboration. I will focus on this particular paper, number 20, cosmology from SZ cluster counts. This is one of the 88 Planck articles from the 21st March release. It's also one of the 18 Planck article on SZ science from 2011. It's based on the largest SZ sample selected from the Planck SZ catalog that Monique just discussed. And the goal, as the title said, is to make cosmological constraints from SZ cluster counts. It's the first article of a series focused this time mainly on counts in redshift only and mostly on lambda CDM parameters. So what you need when you want to do cosmology from cluster number counts, you need a sample first, and then you need to model the counts as described here. For this, you need to assume a mass function. In our case, we assume as a reference mass function the Tinker et al. Mass function. You need a scaling relation from which goes from the mass to the flux, the y flux in SZ. For this, we used the scaling just described by Monique based on 71 Planck clusters. One of the key points is to have the right selection function. Again, for this, we used the Planck noise map to deduce analytical selection function. And then, obviously, we need a reference sample which we decided to build by doing a signal-to-noise cut, leaving us with 189 clusters. We tried as much as possible to have consistency in our analysis using mostly Planck information. That's why the scaling is based on Planck clusters, the selection function of the noise maps. And we will check as well, I will show how the constraints are moving or not, depending on the reference or alternative assumption that we have. So for the scaling, this is a plot shown by Monique. You have here 71 clusters, and then the scaling relation between the flux y and the mass yx. For comparison, you have in red what was published in 2011 in the early papers, PEP 11. And the reassessment with more clusters and better data in black, and you see that there's not much change between the two. So from this scaling, basically, you have this relation between the flux and the mass. This gives you the slope and also the scatter in y and some calibration y star. But what we want is a relation between the y and the true mass, not only the yx mass. So for this, we used the ratio between our scaling and available scaling relation based on numerical simulations from the literature. And what we found is that basically when you do the ratio, you have a full family of different scalings from simulations. And we found that the median value is 0.8, and it spreads in the range 0.7 and 1. So basically, having this bias and y star, we have the calibration of the scaling relation between the SZ flux and the true mass. For the selection function of the completeness, when we are using the noise map given by the detection method, in our case it was the multi-match filter method, you have here a representation of the noise depending on the position of the sky in different square patches, going from 0.5 in blue to 2 times the median noise in this map. The thing is that the noise is varying with the size of the filter. So basically what we have is an estimation of the noise depending on the filter size and the location in the sky. And then from this, we built an analytical completeness using a F function, and where X is your signal-to-noise cut. And you have here a representation of this analytical completeness in dashed line, in blue and greenish, for two different sizes of the filter, 6 arc minute and 15 arc minutes. And you see that obviously it goes from 0 to 1, but we take into account all the way all the range between 0 and 1. We have also an alternative completeness based on numerical on Monte Carlo simulations, and this is the blue and green dots with error bars. And you see, for example, that for 6 arc minutes, the two are agreeing perfectly, and there's a slight change between the two at higher filter size, and we will see the effect of this in the rest of the talk. Then you need the cosmological sample, but before this I'll just say a word on the Planck SZ catalog. As Monique said, we have now the full sky, almost full sky SZ catalog. It's based on frequency from 100 to 857 gigahertz with 3 different detection algorithms, and it covers almost 84% of the sky. So this leaves us with 1,227 clusters and candidates with the different ratio of known, new clusters confirmed by us, and candidates. Typically, for those for which we have the redshift, they go from 0 to 1, and in mass from 1 to 20 10 to the 14 solar masses, with a medium mass of 3.5 10 to the 14 solar masses. And I encourage you to read the paper number 29 and to download from the Planck Legacy Archive the full catalog. So from this, we are building a cosmological sample, which is a compromise between having a high purity and a large number of clusters, especially with redshift, because we are doing the number counts in redshifts. For this, we selected only the 65% cleanest part of the sky. You see that the mask is larger now. And we adopt a signal-to-noise cut of 7 in the MMF3 method, giving us 189 clusters. From these, we have 188 redshifts, among which 184 are spectroscopic redshifts. And among these, 71 are used for deducing the scaling relation. So basically, we are building a well-characterized SZ selected sample, and you have here the number counts as a function of redshift with the red points and error bars. So we have now the sample, we have the model, we can compare the two and have constraints on cosmological parameters. So I show here two results with two different priors, SZ plus HST and SZ plus BAO. Here I focus on omega m, sigma 8 and H naught, but NS, omega b, and the 3 scaling relation parameters are marginalized over. And for this run, we adopt the value of 0.8 in terms of bias. So what you see is, as previously shown, that basically the two priors prefer different value of H naught. But if you look at the constraints on sigma 8 and omega m, basically the constraints are quite similar. Especially if you look at the degeneracy line between sigma 8 and omega m, you see that the two ellipses are in really good agreement, and they follow this blue line, which is sigma 8 omega m to the 0.3, which is a common degeneracy in SZ surveys. So here are the constraints that we have using these two priors. And now we want to know how this is robust when changing the different assumptions that I was showing in the beginning. So from the rest, I will call reference run the SZ plus BAO. I'm showing here different runs with different assumptions. And every time the red contours are the reference run with the 2 sigma level contours. So the first thing we did was to change the sample. Instead of cutting at signal to noise of 7, we cut at signal to noise of 8 to be less sensitive to the selection function. And this is the blue contour that you see here. And basically, it has no effect on the constraints. Then we use a different detection algorithm, MMF1, for which we have almost the same clusters, but the noise is different because the patch are different and the noise estimation is different. And this time you have the black contours where you see a small shift in terms of sigma 8, but the constraints on omega m are exactly the same. And then we use an alternative way of computing the completeness based on Monte Carlo simulations. And this gives you the purple ellipse, which is a bit larger in terms of omega m, but again, it's just moving along the degeneracy line sigma 8 omega m to the 0.3. Then we can change some modeling assumptions. We use the scaling relation, but keeping fixed the evolution in redshift to the self-similar 0.66. And now we allow this evolution of the scaling to be free, completely free, and you end up with the blue contours here. Again, the things are a bit shifted and elongated, but always along the degeneracy line, and the width is almost the same as before. Then we changed the mass function, and we adopt the Watson et al. Mass function, which is more sensitive to high mass clusters, which we have in our sample. And this time, you see that the degeneracy line is a bit tilted compared to the usual one, but the contours are well in agreement with what we found with the Tinker et al. Mass function. Then remains our biggest systematic, the bias, the relation between the true mass and the mass estimated in X-ray with our scaling. And instead of fixing it to 0.8, we leave it free between 0.7 and 1, which is the range of the different numerical simulation that we had. And this time, it enlarges a lot the error bars, especially in the sigma 8 directions, because the bias and the sigma 8 are correlated. But the constraints on omega m are not moving that much. So we have some consistency in our analysis and some robustness. I won't ask you to read everything, but basically the number doesn't change much within the 2 sigma error bars that we have in the reference run. And if you allow the bias to be more free, obviously you have larger error bars. So do we have a coherent view among clusters? Well, we compared some of the recent findings on cosmological constraints with ours. I'm plotting here the constraints on sigma 8 omega m to the 0.3, which is really the degeneracy line that we managed to constrain. With Planck, systematic and statistical and systematic error bars. By systematic, I call the case when we leave B to be free between 0.7 and 1. You have constraint from SPT, ACT, using the same pressure profile that we used, and ACT with different scaling laws and pressure profiles. Max BCG based on 70,000 optical clusters, and X-ray constraints with like 90 X-ray clusters. And you see that it's almost a good agreement between all constraints coming from clusters. Now, how does it compare to CMB? As you see here, constraints in terms of omega m and sigma 8, SZ plus BAO, CMB. Tends to find higher sigma 8 and higher omega m. This is some kind of 3 sigma tensions between the 2 probes. If we come back to the counts, you have here in red the observed number counts in redshift. In blue, the best fit model we find from the clusters. And in green, what is predicted, assuming the cosmological parameters from CMB and a bias of 0.8. And you see that we have almost half of the clusters missing. And if we put the constraints in terms of sigma 8 omega m to the 0.3 again, you see the discrepancy between the 2. So is it just general between clusters and CMB? We have to dig into that. So how can we reconcile the 2 probes? Well, there's 2 ways. The first one is to find some process to get higher value of sigma 8 from clusters. For this, you can change the scaling, you can change the bias, you can account for some of the missing clusters that we didn't account for. The other way is to get a lower sigma rate from the CMB. For this, you can, for example, change the initial power spectrum or change the transfer function. So how does it go? Higher sigma 8 in clusters. Well, one thing we did was to combine the two, SZ and CMB, but leave the bias completely free, not anymore between 0.7 and 1. And you have here the black contours of the combined analysis, finding a bias around 1 minus B around 0.55. So if you decrease the bias to 50% or 45%, then you can reconcile the two. But it opens a question about what happens to these baryons, because X-ray and SZ are probing the baryons, and they don't seem to follow the dark matter, because we may account for only half of this. Then we checked for the missing clusters. We know that some big clusters are not accounted in the SZ catalog, Planck SZ catalog. We know that we are masking point sources that can be correlated with SZ clusters, but it doesn't explain the 100 and something cluster that we are missing for reconciling the two. Other solution, lowering the sigma 8 in CMB. We tried to change the running of the initial polar spectrum. It's not enough to make the two agree. Another solution is to put massive neutrinos. So you have here different runs of combined CMB and SZ when you leave the mass of the neutrino free. And depending on the prior you take on the BAO or on the bias, you find different values of the massive neutrino. So here, having a low bias or high bias and a massive neutrino are two of the possible solutions that reconcile the two. So I will just conclude. I've shown you that we have cosmological constraints from these 189 selected clusters. We are limited by systematic mostly, not by statistics. We have some robustness of the results with respect to the theoretical assumptions and the sample that we've been using. We are in agreement with some other cluster studies, including other SZ cluster studies. We have this tension with Planck CMB, which can be alleviated using a higher bias neutrino, or maybe both, or anything else to be think of. And we have an agreement with the Planck SZ power spectrum that will present in 1 minute. In the perspective side, well, now we can use more clusters. We have more than 189 redshift in the Planck SZ catalog. We can go, for example, to something like 400 clusters by lowering the signal-to-noise ratio. Not only we have more clusters, but obviously by decreasing the signal-to-noise, you get to higher redshift clusters, which have more weight in the cosmological constraints. We can use not only the count in redshift, but now we can use the count in mass or in YZ proxy, as Monique presented. So having, again, you need clusters with redshift, so it's almost the same sample that we can use now. We can test extended cosmology, not only lambda CDM. Obviously, we are still limited by the scaling and bias, so we need to work on this, obviously. And if the discrepancy remains between CMB and SZ, then we have to understand the difference between these low and high redshift probes. And I will stop there. Thank you.
Thank you. We have a couple of minutes for questions. Everything was clear? I think there is... Could you please use the microphone, which is...
How much does the scatter of the YZ mass relation enter
the scatter, you said?
Yes, the scatter.
The scatter. Well, we define the scatter by using the scaling with these 71 clusters. If the scatter is bigger than what we assume, then we will predict more clusters. So even a lower sigma 8.
Okay.
So regarding the issue of whether changing the bias could explain resolve the tension between the Planck and the other results, how much freedom do you really have in that? What is the independent constraint?
Sorry.
What's the independent constraint on the bias? It's instead of just being a number that.
Well, there's not much direct constraints on this bias. Every time there's a measure compared to simulations. Basically, I don't know. I mean, from the simulations mainly.
What are the difficulties to use the same sample of clusters, the same X-ray observations and observations of Planck to get information about the Hubble constant at different redshifts? You have a lot of clusters. Just to get information, additional information about Hubble constant.
Yeah. Okay.
Or distance.
Well, obviously, if we manage to have for the same sample or relative well-defined sample both X-ray and SZ, we can combine the two. I mean, the H0 dependency information from the ratio between the X-ray flux and the SZ. Is it what you think about?
Yes,
yeah,
but
yeah.
why you are not doing this?
No time yet.
Okay, thank you.
Okay. Maybe last question. Yes.
So in the analysis, we treated B as a parameter and marginalized over it. But of course, in fact, it's a stochastic variable. The ratio of the estimated mass from X-rays to the true mass varies from one cluster to another depending on the cluster structure. And so it seems to me that, in fact, we expect the scatter to be quite large between very regular clusters which have a high X-ray luminosity for their mass and very irregular ones which have a low X-ray luminosity for their mass. And so the fact that we need some average value of this to be low doesn't necessarily conflict with the fact that for the clusters we've observed well, which are the regular ones, it always comes out to be relatively high. And this also has an effect for the problem that you said, whether this means we have a problem with the baryon ratios, because the baryon ratios are measured well almost always in the clusters which are quite regular. So those are the ones where the B value would be high. So it's not obvious to me that there really is a contradiction here.
Not necessarily, but I mean, two things. On the scaling, if I can come back to... It's true that most of the study are done with regular clusters. But the additional ones, which is Planck XMM validation, that are the green dots here, are purely SZ selected. So some of them are not so regular clusters. And they fall more or less well in the scaling. So it doesn't mean that all of them do, but at least the one in the sample. And one next step that we can do is, instead of separating this 1 minus B, as you said, as an average thing, we can have this the product of these two as a free parameter for each cluster.
I understand, but the plot you have up here just shows that the SZ measurement correlates very well with the X-ray measurement. It doesn't show that the SZ measurement and X-ray measurement correlate very well with the true mass.
Yeah, agreed.
Okay, I think we have to move on. With thanks again, Marion, for the talk. So